Okay, let's start.
Which is f of x derivative.
So we're still in 2.3, 2.4.
Yeah.
Let's just recall some of the things we looked at so far. So one thing I have to recall is that there's this new function that's defined in terms of a limit. This is what we call the derivative. It's equal to the derivative of f of x. And x is a measure of the slope of f. At x is also a measure of the slope of the tangent line. To f at x, which is a good approximation in some situations, so that's one of the reasons why this is very useful. It's also a measure of the rate of change of f at x, which is kind of a measure of speed, or how fast f is changing. We also looked at the second derivative. This is f double prime. This is how fast f prime changes. And we saw that this was a measurement of concavity, which has its own interpretations. We can talk about how a graph is curved, can tell you something about the graph. Whether it's increasing or it's increasing at an increasing rate, decreasing at a decreasing rate, or vice versa, it has all sorts of mixtures. So just to remember, again, some notation, just to make sure we're all on the same page with this. So if you have f prime, or you can have y prime, or you can have dy dx, or you can have d dx of some function. This is called the first derivative. And these are notations for this guy. And of course, if you have f double prime, or y double prime, or d squared y dx squared, or d squared dx squared of some function, that's called second derivative. And you should just remember that's just the derivative of the derivative. So that's where we've been so far, and we've been talking about these very conceptually. We're still going to talk about a lot of ideas today, but in the next class we'll start to actually do some computations, prove some nice rules that will allow us to talk about these guys in an easier way. But so far that's kind of where we are. And I sort of want to continue this. I want to look at an example where the derivative is not defined. So the idea, of course, here is the derivative is a limit, right? And it's possible for limits to not exist. So yes, the derivative is useful. Yes, it's a lot of the reason why we're here in the first place, but there are times when it does not work. I want to discuss these times and what they can hint to us as well. So here, let's consider an example. And then I'll discuss some situations. Let's look at this function, absolute value of x. we're going to attempt to find the derivative when x is 0 for this function. And spoiler alert, it's not going to work. This is when the derivative does not exist, is what we're looking at. So recall that f prime is just the limit as x approaches 0, f of x plus h minus f of x h. H equals 0. Okay. So if we want to find the derivative at 0, we're literally going to just plug in x equals 0 into our formula. And you can find the derivative of 0 right away. So if our function is the absolute value of x, what is f of 0 plus h? What do I write down here? What's f of 0 plus h? If f of x is absolute value of x. Absolute value of 0 plus h. Minus absolute value of 0 all over h. What's the absolute value of 0? Well, it's just 0. So this is just the absolute value of h over h. Now, what is that limit? Do you guys remember how to deal with absolute values? Like, what does it mean to take an absolute value? How do you define the function absolute value of x? Do you remember what it looks like? Yep. It's a v. So it goes like that. And then it goes like that. So what's the definition on this side? It's just y equals x, right? That's y equals x. And what's the definition on this side? It's y equals minus x. So the absolute value of x is a piecewise function. It's x if your x is positive. It's minus x if your x is negative. Right? So this is a function that always takes your distance from the origin. Another way you can think of it is it always makes negative values positive. So take anything that's negative, it'll flip it on top to make it positive. Right? So that's why whenever your x is less than 0, it takes the negative of your x to make it positive. And so that's your absolute value of x. So your absolute value of x actually has two definitions. And so this limit will actually break into two parts. So it's possible to be two things. If we're coming from the left, this is just going to be minus h over h, because we're less than 0. Right? So that's going to equal to 1. While if we're coming from the right, that's just going to give me back h. That's just h over h is actually equal to plus 1. So because if we're coming from the left, we get a negative. If we're coming from the right, we get a positive. What does that mean about the limit as h approaches 0? It doesn't exist. In other words, the derivative does not exist at x equals 0. It's impossible to find a derivative at the point x equals 0 for the function absolute value of x. Now, one of the reasons why is that we can see graphically is there's a sharp corner. And there are challenges to drawing tangent lines at sharp corners. Right? Your absolute value of x has a sharp corner at 0. Now the thing is, if we want to draw a tangent line to this function through that point, what would the tangent line be? It turns out it could be a bunch of things. I could draw a bunch of lines passing through that point that will locally touch the curve at one point. They will all qualify as tangent lines by our definition. So the tangent line is really undefined because you can't really draw a tangent line. There's no way you can actually zoom in so that a straight line looks like a sharp corner, right? So the tangent line was just a line that when you draw it through that one point, when you zoom in, the function and the tangent line looks pretty much the same. It'll never look the same. The straight line is never going to look like a sharp corner. So that's one of the reasons geometrically why we could have guessed that the derivative would not exist at this point, but you can also prove it by going through the limit definition. Similarly, so i.e. the derivative will not exist at a point if we cannot draw a tangent line. So the short story is we developed this formula, this general formula, when we're trying to draw a tangent line to a curve. And that could happen if when we zoom in, the tangent line and the curve are pretty much doing the same thing. And so basically what that means is derivatives will not exist at any point of a function if when you zoom in, it doesn't look like a straight line. If you cannot draw a tangent line there, the derivative will not exist. And you can use this sort of this computationally, but you can also see this graph just by looking at pictures. And this is something I will be asking you in the future. Oh, here's a graph. Tell me where the graph is not differentiable, or where you cannot define a derivative. Or tell me where the function is not continuous. We talked about continuity before. So now we're also going to talk about differentiability of functions. So this gives 3 situations in which derivatives will not exist. This idea can boil down to 3 situations. So there are 3 situations in which differential calculus will not work. You can't use calculus to answer whatever question you want to answer. One is at points where there is a cusp. Cusp is a fancy mathematical way of saying sharp point. That's how math people call sharp corners. They call them cusps. So if there's a sharp corner like this or this, right? Anything like that, you cannot find derivatives at sharp corners. It's impossible. And again, why? You can't draw tangent lines at sharp corners. You cannot zoom into a sharp corner and make it look like a line. Second is if the function is discontinuous at a point. I believe I've defined the word discontinuous. It just means not continuous. At at the point. So if there's like a hole, or there's some sort of asymptote, or there's like a gap, otherwise. All right, at all these x values, if you were to draw like I'm just putting in random axes here. So these are all not differentiable. At x equals a, i.e. we cannot find derivatives. So derivatives will not exist at sharp corners. They also will not exist when your function is not continuous. You can't draw a tangent line to a point if there is no point. And a hole will never look like a straight line if you zoom in. Third situation, derivatives will not exist. This is at points where the function will have vertical tangent lines. There are examples of functions that do something like this. Say this is x and y. So the function will be going along, and then it'll go vertical for a split second, and then switch concavity and go here. And if you were to zoom into that point, it turns out it would kind of start to look like a vertical line as opposed to any other kind of line. So the best tangent line is actually a vertical. But that kind of means, so it's vertical, and we know for vertical, this means that the slope is undefined. Therefore, the derivative is undefined, because the derivative is the slope. Yes?
So on the test, will you ask us to list what are the three
more than likely, if I ask you a question about this topic, which it won't be a main focus, it'll probably just be like one problem thrown out there. I would actually give you a graph, and I would say, for what x values can you not find a derivative? For what x values is the function continuous versus differentiable? So I can give you an example of such a question that I might ask. And then after this, I kind of want to do a summary of what each of the functions, similar to the table that we did on the quiz. I want to actually do a big table for you that talks about the different kinds of functions and the information they give us. But it's important to know that there are times when the derivative does not work. So I can give you an example of a problem that might come up, something like or state. Semicircle. That's supposed to be a semicircle. Let's say this is one, two, and this is the function f of x. So you can imagine it's some sort of piecewise function. So what would you say? Where's our function not continuous? Yeah?
7 and 10.
7 and 10. Otherwise, this whole time, I could draw the function without lifting my pencil off the page. Once I get to 7, though, I have to lift my pencil because there's a gap. I also have to lift my pencil because there's a hole and there's an asymptote. So x equals 7 and x equals 10 are points where this function is not continuous. So where is the function not differentiable? Okay.
5, 7.
Well, discontinuity, one of the easiest ways to get to some answers here, which I've seen students leave these out, these are the easiest ones. If you know where it's discontinuous, that's automatically a point where it's not going to be differentiable. So 7 and 10 are automatically copied down here, but there may be others. All right, so differentiability is harder to obtain than continuity. Yeah, so you said
5, 7,
5, 7, and 10. So we also have x equals 5. Are there any more? Yeah?
X equals 1.
Huh?
X equals 1.
At 1 as well. This is a sharp corner here. All right, if you zoom into that, that's going to be a corner. It's a horizontal line hitting a semicircle. That's going to create a sharp corner, so x equals 1. Yeah.
Can you just define differentiable again?
Oh, differentiable means we can take the derivative. This means f prime exists. We can take derivatives, we call it differentiable. It's sort of the objective.
Also, technically for this one, negative numbers too, right? Because there's no graph there, in theory. Like on this one.
I can just, sure, but let's just say I say the domain of f is, x greater than or equal to 0. In which case, I don't worry about the negative sign. So yeah, that's basically it. So there are times when you're looking at functions, there are places where you cannot use calculus to answer certain questions. There are many applications to calculus and many questions we can answer, but there are times when we can't actually use calculus to help us, and these are 3 situations in which we can't do it. So now let's sort of summarize. Summarize some important ideas here that we will be using as the semester goes on. Say, here's our function. It tells us about be on this side. Third column. How it tells us. So, say we have our function f of x. Nothing strange about that. We've been dealing with functions for a long time. We kind of know what they're all about. They give us output values for a specific rule. So this tells us about output values for a rule. It also gives us points on the graph. How would it tell us? Well, we already kind of know that as well. So we know that if y equals f of x, then y is the output, and the point x comma y is on the graph. So if you can plug in x, find y, is how you actually derive that information. So if you're ever in a situation where you want to figure out what is going to be the corresponding output for some input, or what is going to be a point on a graph, right? So for example, if we're finding the equation of a tangent line, one of the things we need is a point on the tangent line. If you need a point on a graph, you use the original function. You will always use the original function. You'll never use any other kind of function to find a point on a graph. Now we've learned a different kind of function called the derivative. This is f prime. And that function also gives us important information. But it does not tell us about points on a graph. It tells us about completely different things. For one, it can tell us if our function is increasing. It can tell us if our function is decreasing. And hence it can tell us about maximums and minimums. So if you're studying a function, you're studying some rule or some data or some output, and your goal is to figure out, is my data increasing? Is my data decreasing? Where is the maximum point? Where are the minimum points? When is it as big as possible? When is it as small as possible? The first derivative is the function that is going to give you that information. You would not look at the original graph for that information. You would not look at any other function for that information. You would look at the first derivative. This is what its point is. This is what it tells us about. It tells us about slope, but slope can tell us about increasing and decreasing. And it can also tell us about maximums and minimums, because if you're increasing and then you start to decrease, surely you hit a maximum at some point. And vice versa for here. So how it tells us? Well, if we can figure out where the derivative is positive, that means it's increasing. If we can figure out where the derivative is negative, that means it's decreasing. So a function is increasing when the derivative is positive, it is decreasing when the derivative is negative. As far as maximums and minimums go, here's how we can obtain a maximum. Let's say we have some point here, x equals a. If we're increasing on the left, this means on this side f prime is positive. But we're decreasing on the right. And at a, f is continuous, and f prime is 0 or undefined. This would mean f of a is a maximum. So you kind of put a few pieces of information together. You have to find out what the derivative is on the left of the point and on the right of the point, and at the point what's going on, and that will tell you if it's a maximum or a minimum. You can squeeze this in. I think in your notebooks you'll probably have more vertical space, but I'm going to squeeze this over here. Minimum is pretty much the opposite. So see, if you're decreasing here, then you're increasing. So your f prime is less than 0, f prime greater than 0. And here your f is continuous. Your f prime is 0 or undefined. That will be how you identify minimum points on that. So like I said, there's no vertex formula for general functions. In general, if we want to find maximums and minimums, we go through a whole process that's led by the derivative. We've then covered the second derivative. This also tells us some information. This tells us about concavity. It also tells us about inflections. So if you're looking to know what the concavity of your function is or where the inflection points are, you would look at the second derivative. You would not look at the first derivative. You would not look at the original function. If your goal is to figure out these two, this is the guy that you're looking at. And similarly, if this is positive, that means concave up. That means up like a cup, that's the shape. If it's negative, that's concave down. Down like a frown, means it shapes like a frowny face. And inflection is where concavity changes. So here's A. If our function is continuous and the second derivative is 0 or undefined and changes sign on either side. Then f of A is an inflection point. So we'll stop there. We've done enough for 2.3 and 2.4, so the homework for that is due next class. But yeah, it's going to be very important knowing what each kind of function, what information it gives you, and how to get that information, extract that information. And next time we'll start some fun stuff. We'll look at some formulas to find
It's a lot.
fun again.